let's work through these. See where we got. Good understanding so far. Okay, A. Someone tell me how they got to the answer. What's the answer? Yeah.
0.
Yeah, you just plug in, right? There's actually nothing wrong with plugging in here. It's a fraction, so one thing you should be worried about is the denominator being 0, but the denominator is x squared plus 1, that's never 0. Right? You can know that from the graph of x squared plus 1. It's just a parabola shifted up. It never touches the x-axis, so there's nothing wrong with just plugging in. So strategy 1 helps us here. So the limit as x approaches 1, x minus 1 over x squared plus 1 is just going to be 1 minus 1 over 1 squared plus 1. 0. Okay, E. Okay, how did you do that one? Did you?
Yeah, I can.
You also did this, okay?
For this one, you couldn't plug in, so I simplified and then plugged in.
Right, so plugging in 1 here, you divide by 0, so you can't plug in. So you start to simplify, keep writing the limit sign while you're simplifying. Assuming you simplified the denominator, what did you get?
I got 1 plus x and 1 minus x.
Okay, then?
If you factor a negative out of the top, then you get the 1 minus x that you want. And
Okay.
they cancel, and you get negative 1 over.
Okay, so this cancels into that negative 1 times, right? So you end up with the limit as x approaches 1 of minus 1 over 1 plus x. And then?
And then you can plug in now, so
Now
now
you
you
can
negative half.
Yes, exactly. Good. Plus 1, x squared minus 1. Yeah, let's see. Okay, what happened here? Yeah?
I just have a quick question about B.
Oh,
I remember
sure.
last class when we did one in a similar manner to that, we had to write, but x does not equal 1 because we can't, when we factored and canceled in one last class, we had to say
I
x.
wrote that for emphasis, but in general, for some
It
items,
doesn't
you
need to
don't
be
have to say
written.
that,
Okay.
because the limit already has the idea
Yeah.
of, we don't care about
Yeah,
being there.
right, but you don't care if we write that or not?
Yeah, no. so-
Okay, cool.
Like, how I'm writing it out now is
It's fine.
perfectly acceptable.
Sounds good.
Right, the limit already kind of know, people already know that, hey, yeah, it's a limit, so you might not actually be there, it's fine.
Okay.
Yeah, so, did anyone do this one? You did it? What did you
Yeah.
get?
I simplified it a little more so I can graph it a little easier.
Right, so obviously plugging in is not gonna work, so you might think that, hey, maybe it's like B, you can simplify, what does this become?
X plus 1 and minus 1.
This cancels right away, and so we have this. Okay, now what?
Yeah, it's like the same graph like this, but it shifts over one to the
Right, so now you simplified, and you realize, hey, I still can't plug in, so what do? So now you have to use another strategy. Probably the easiest strategy here is just do the graph, because that's just like taking the 1 over x graph and shifting to the right by 1, right? Something we would know from algebra, right? So this just means x equals 1 is like the new y-axis, and you're shifted here. Okay? So knowing that, what do you say the answer is?
It does not exist.
Does not exist. Now, I never asked this here, but I should point out at this point that had I asked you from the right, put a plus sign here, the answer would be infinity, right? And if I had put from the left, the answer would be negative infinity, right? But just to put limit as you approach 1, it does not exist because your y values disagree. Okay, D. Who did D? Okay, how, tell me your reason.
It's approaching -1 from the left side and approaching 1 from the right side.
How do you know?
Logically, like it's x divided by x, so when it's a small negative number, the top becomes a positive number, so it approaches -1, but when it's positive, it approaches 1 because it's
Okay,
I don't know.
so here, seeing absolute value of x, you should remember what that means. So you want to recall what absolute value of x means. It just gives you the number inside if your x is not negative, and it gives you the negative of that if your x is negative, right? So it takes the negative of a negative number to make it positive. Absolute values wants to give you the distance from 0, so it always wants to keep things positive. So you'll notice that, remember that the graph looks like this. You'll notice that on the right side, you have the graph y equals x, while on the left side, you have the graph y equals minus x, right? That's this graph, and that's that graph. So knowing that is happening, so on either side of 0, you should realize that something else is going on. So there are many ways you can express this, but I'll just kind of write it out using this definition in mind. You can realize that, well, there's kind of an issue here with the absolute value of x approaching 0, because this is like asking me the limit as x approaches 0 of x over x when my x is positive, right? So in other words, approaching from the right, that's the function. However, if I look on the left side, that's the function, right? Now, of course, you can simplify, and you'll end up with, well, it's a positive 1 if I'm on the right side of 0, but it's a negative 1 if I'm on the left side of 0, and that implies it does not exist. If you want to know what the graph of this looks like, well, it kind of tells you. When you're on the right side, it's just y equals 1. When you're on the left side, it's just y equals minus 1. So the y values do not agree, they don't connect. And you have to remember how the absolute value function behaves in order to know. E. This is just another notation, if you forgot, for tangent inverse. And remember, that does not mean 1 over tangent, that's a notation for the inverse function of tangent. Okay, so what do we do here? This is probably more pre-calculus instead of college algebra, I would guess. That's where you would have really studied trig functions and inverse trig functions. What do you know about the tan inverse? How do we do this? Yeah? Yeah?
I think it's like a sideways cubic,
Yeah?
so I think it would level off at 1. Is it 1 to infinity? Maybe?
Close. So here, yeah, plugging in and simplifying doesn't seem to work out, but if you remember what the graph looks like, yes, there is an upper bound and there is a lower bound, and it kind of looks like a sideways cubic. Well, if you turn your head this way, it's like the negative cubic. Yeah, it looks like this. Now, if you remember where the tangent itself is defined, remember tangent is sine over cosine, so it's undefined whenever the cosine is 0. Remember where cosine is 0, that's pi over 2 and minus pi over 2. So that's the tangent inverse graph. So knowing that graph tells us this is
Pi over 2.
pi over 2. So you can just draw that picture and see it from the graph. colored chalk that erases nicely. Look at that. Yeah,
How do you do that without knowing the graph? You can't.
at this point you can. You would have to know the graph. Yeah, there's no way around that. Like, you don't have a nice formula that you can plug in for tan inverse. It's just kind of something you have to know how it's constructed. So you pretty much take the tangent graph and ignore everyone except the center point and then reflect in the line y equals x. Right? So you kind of learned that in pre-calc. You should know the graph, and I'll expect you to know the graph. The graph is the best way. To find a kind of formulaic way to think about the tangent, you won't really do that until Calc 2, Calc 3. And even then, a problem like this, I would think of the graph. So the graph is, thinking about the graph is really the best way to do this. Anyone get to this one? Yeah?
You can't plug in, so I rationalized.
Right, you can rationalize, and you rationalize by multiplying by the conjugate over itself. So you multiply by something divided by itself, so you multiply by 1. So here we multiply by, what did you multiply by?
The square root of 1 plus 3x plus 1.
Plus 1 over 1 plus 3x plus 1. And this is called a conjugate. It's another algebra thing. You should know how to rationalize and simplify things of this form. That being said, remember what happens. Why you do the whole rationalize thing is to take advantage of the, well, in the top, we just have this. And the bottom is where we really needed the simplification. And you can realize you have this times this times that. And this works out very nicely because it takes advantage of the difference of squares formula. This looks like a minus b times a plus b. So you know that the answer should be a squared minus b squared. A minus b, a plus b. So you know the answer should be a squared minus b squared. Right? So you take this squared, which just gets rid of the radical, minus this squared. 1 squared is just 1. And so now, the 1 cancels the 1, minus 1. Here we have 3x, the x's will cancel the x, and now we can actually plug in 0. So that would just become the square root of 1 plus 1 over 3. So 2/3 is the answer. Okay, we get here. Yeah.
Don't we only count like the highest powers, so it would be 1 over infinity, and then 0.
Right, it's 0. You could say, because it's no, top of B, bottom of B. Right, remember last class I told you how the different functions relate to each other, and we know that x to the a is much smaller than x to the b when your x is going off to infinity. Which means the highest powers are going to control the function. Compared to these guys, no one else matters. Everyone else might as well not be there. Now, if you only focus on the highest powers, Now you realize you're looking at something that looks like x cubed over x to the fifth. Well, you can simplify that to something that like 1 over x squared. And so now you have something that is behaving like 1 over x squared as x is going to infinity, and that will give you 0. Right? So that's just a bottom-heavy function, just understanding how functions work. Now this I'm going to show you just because there are people who would complain if I didn't show you, but I don't particularly care. One way to actually, a more computational way to see that this happens is, well, for me, you writing 0 and saying it's bottom heavy, that's good enough for me. That's you showing work as far as I'm concerned. I like when you can make quick judgments about functions and understand what's going on. A computational way, and this will work for G, H, and I. Right? Whenever you see a ratio of polynomials like this is something you can always do, is you can divide each term by highest power of x in denominator. So if you see something like G, highest power of x in the denominator is x to the fifth. So I clearly go through and divide everyone by x to the fifth. And so at the end of the day, you'll have 4 over x to the fifth plus 1 over x to the fourth minus 1 over x squared over 2 minus 3 over x cubed plus pi over x to the fourth plus radical 2 over x to the fifth. Now, based on your idea of limits, it should be clear that as these guys, all the numerators are now constants. So if the numerator is a constant, the denominator is a variable that's going off to infinity, these guys are all going to go off to 0. And so basically you end up with 0 over 2, which is 0. It's a computational way to do it. But having the idea that the largest powers control the function as you're going off to infinity, is the nice way to do it. That being said, what about H and I? So again, the idea is look at the largest powers. Now clearly, that looks like something that's going to behave like x squared, right? But, so we know the answer is going to be infinity. The question is, plus or minus is our options. How do you figure out which? Is it positive here or negative? Yeah?
Or positive.
Why?
Minus 6 times negative number.
Right, plugging a negative number into something with an odd power, that becomes negative, multiplied by minus 6, right? So that's a negative times a negative, so the numerator is going off to a positive number. While here, if you do the cube of a negative, that becomes negative, you multiply by a positive 2. So divide by a negative number, and so Negative infinity is the answer. So in the highest powers on the top, you kind of have to watch the signs a little bit and be careful. So according to this one, you'll have a very large positive number divided by a small negative number. And so you'll end up with a very large negative number. And again, you could do that whole thing of dividing the denominator, dividing the top and bottom by x cubed. You'll notice that you end up with a constant on the bottom and a power of x on top, which is going off to infinity, and then you can watch the signs carefully again. This one I will refer to as top-heavy, as in the bigger function is on the top, so it's going to overwhelm the denominator and go off to infinity. And you could go through something like this again, but I won't. What's up? Yeah?
Take the highest powers of both, they cancel each other.
So you can literally ignore everyone. They're effectively zero. I don't know how to write that, effectively zero. The notation of that. But you pretty much ignore everyone except the highest powers. So you expect this thing to behave like 17x cubed over 2x cubed. So the x cubes would cancel, and ultimately you end up with minus 17 over 2 as the answer. And to show work, you can say, the catchphrase for this is ratio of leading coefficients. Wherever the powers are the same, the numerator and denominator will grow at the same rate, whatever that might mean at this point. And in that case, only the coefficients matter. These are the leading coefficients, they're called, the coefficients of the x with the highest power. It's called the leading coefficient. So you take the leading coefficient of the numerator, divide by the leading coefficient of the denominator, and that's going to be your answer. I want to officially summarize the idea used here. This is limits at infinity of rational functions. Technically, you don't only have to apply these to rational functions, but you can apply it to anything, any of those functions that I gave you in that long relationship in the last class. Just knowing who's bigger than who as you're going to infinity, the same principles kind of apply, but ratio of leading coefficients would kind of apply here. So assume your P of x, Q of x are polynomials. Of course, your Q of x not equal to 0. Then the limit, whether you're going to positive or negative infinity of P of x divided by Q of x, it almost doesn't matter. there are only 3 cases that could happen with a function like this. One, you can get 0 as the answer. This is the bottom heavy case, and this is if the highest power, which is called the degree of Q is larger than the degree of P. This is degree of Q. This is the largest power. So if you're faced with a limit that looks like that, you notice that the highest power is on the bottom, the answer is going to be 0. And it's bottom heavy. Another option is you can get plus or minus infinity. This is if the degree of P is larger than the degree of Q. And you have to watch the signs. To know if it is plus infinity or minus infinity. And the other option is leading coefficient of P divided by leading coefficient of Q. And this is if the degrees are equal. So this you can refer to as top heavy. And this is just ratio of leading coefficients. So functions like that have only 3 cases. And it's easy to tell which by just ignoring everyone except the highest powers. Got a lot of mileage out of this. Let's see. What do we want to talk about next? We don't have much time left, but maybe I'll just write down some notes and put some examples on the board and have you guys try them, and you guys can tell me what you get on Tuesday. That's probably good. By the way, this is where last week when I mentioned the special techniques, this is one of them. We're kind of talking about special techniques now. We're kind of in that section. So this is the special technique from step 3 of the strategy. Here are other these are actually limits that we can find. They make sense to us according to our limit definitions. Then, here's an important fact. If your f of x is less than or equal to your g of x for all x near a, then the limits will share the same inequality, right? Remember, the limits are tracking the y values as x gets close to a. So if the y values over here are always greater than or equal to the y values over here, then whatever those y values get close to as you get close to a will always be bigger than the y values that f gets close to as you get to a. So knowing the an inequality relationship between two functions near some value where you're taking a limit, you automatically know the relationship between the limits. It follows exactly. Also, this leads to a special technique. Now you can use that idea to prove this idea. Can anyone guess what I'm going to write now? A limit theorem that has an inequality. But you might have seen this before. It's called the Squeeze Theorem. You might hear it first as the sandwich theorem. Not very often, though. Most people refer to it as the Squeeze Theorem. And that is if you know that you have a chain of inequalities. I'm going to put F in the middle. It doesn't really matter though. Looking like this. And you know furthermore that the limit of the h is equal to the limit of the g, and let's say that's some L. Then, right? So this is why it's called the squeeze theorem or the sandwich theorem. You have functions and you know what's going on at the endpoints when when you're taking limits. So you're creating a limit sandwich here with the f. If the limit as x approaches a of the h and the g are both give you the same number, then it turns out that the limit of the f must give you that same number. The idea is you just take the limit of everyone. This relationship tells you that's not going to change the inequalities. Knowing these answers here means you can put in L here and L here. And so you'd have the limit of f is between L and L, right? So if you're less than or equal to something, and at the same time you're greater than or equal to something, the only way those can both be true at the same time is if you're actually equal to the thing. Right? If you're less than or equal to 2 and greater than or equal to 2 at the same time, you have to be 2. And that idea is called the squeeze theorem. Here are a couple examples that you can solve using the squeeze theorem. That's an important thing. You can try those 3 for next time. We'll start next class with going through those examples as well as and I short the squeeze theorem like this. Using the squeeze theorem and some geometry. You can prove. I'm not going to prove it, I'm just saying you can. Right? I'm going to do some proofs in this class, but I want to save my time for the really important ones. skip over these because I'm never actually going to ask you to prove these or know anything about the proof, but you will need to be able to recall these facts. These are the special trig limits. One, the limit as x approaches 0 of sine x over x is, does anyone remember?
One?
It's 1, right? You draw a circle in the first quadrant and then you do a triangle and you do a bunch of stuff with the geometry and then you sort of squeeze these distances and apply the squeeze theorem and you can figure that out. By the way, this implies that the same relationship exists for tangent, because that's sine over cosine. So it's like you take the sine x over x and then you multiply by 1 over cosine. But at 0, cosine is 1, so that still holds. You can get to it very quickly, but it's probably useful to think of it as a second fact. Note that 1 and 2 mean you can take reciprocals here. So you can say, put the x over the sine x, and it will still be 1. You can also put the x over the tangent, and it would still be 1, because you can flip them. And you can use 1 with some trig formula manipulation. I think your book actually proves these, so if you're interested, you can look it up. They're not terribly difficult. A third special trig limit. One minus cosine x over x equals 0. You could also some people memorize it the other way, it doesn't matter. So you might see some people say cosine x minus 1 over x is also 0, but that's just a negative of this. It's the same relationship. And with those in mind, I would like you to also try these examples for Tuesday. We'll stop there, but I have quizzes to give back. So try those 6 examples. We'll kick off Tuesday's class with that. Julia? Matthew isn't here, right?
What?
Nicholas?
Oh, here.
Oh, Michael isn't here. Here. Nicholas, Tiffany, Chris. We'll go to your quizzes. If you got below 70, do not take it lightly. Do not try to rationalize to yourself, oh, I really understand, but you made a silly mistake, or Jhevon's quiz is too hard. If someone else did it, it would be better. Take the number very seriously. The numbers won't lie to you, and you lie to yourself all the time. Go to tutoring and figure out what went wrong, okay? If you're not hitting C average,